Okay, so in this one, we are going to integrate over a piecewise smooth closed curve. So what does piecewise smooth mean? Well, it means that it's made up of a bunch of nice smooth curves that have been sort of glued together at the endpoints. So we have some corners here in particular. We have three corners. We have a corner uh, at 0, 0, at 2, 0, and at 2, 4. So we have three corners here. That's okay. So we're going to go over how you integrate over such things. And our curve is oriented counterclockwise. By convention, we usually want to integrate our curves, we usually want to orient our curves in a counterclockwise rotation. So what we're going to do, let me just make sure my labeling is consistent with the book. Yeah, good. All right, what we're going to do is we are going to label each of our pieces. And then the integral, I'm going to use shorthand. The integral over c of whatever is going to be the integral over c1 plus the integral over c2 plus the integral over c3. So in other words, to compute that integral, what we need to do is we have to compute three separate integrals. So let's do that. To do each of these separate integrals, we have to parameterize our curves. So let me parameterize C1. So C1 has y constantly 0, and I need to walk from 0 to 2. How could we walk from 0 to 2? Well, we let t vary from 0 to 2. When t is 0, we're going to start off at 0, 0, and when t is 2, we're going to end up at 2, 0. C2, what is that going to be? Well, our x has to be constantly 2 when we're on C2, and our y value needs to increase from 0 to 4. So let's do it like this. T goes from 0 to 4. And then lastly, we said when we had the graph of a function, you just sort of plug in y equals x. That's not going to be necessarily true here because we're walking in the other direction. Okay? So what we want to do is we do want to plug in y equals x squared in this case. So we're not going to use t's for this C3. We're going to say, hey, y is x squared. But when we do our integral, we're going to force t to start off at 2, or x to start off at 2, and go to 0, which will make sense when I write the integral down. Because what we want to do is we want to start up here, and then we want to end down here. And starting at x is 2, we'll make sure we do that. Okay, cool. So let's compute each one of these guys separately now. So the integral over c1 y squared dx minus x squared dy is going to be the integral from t is 0 to 2. We're plugging in y is 0 and x is t. Well, if y is 0, every time you see a y, you get 0, right? So there's nothing that's left when we plug that in. And when you integrate 0, it doesn't matter what the bounds are, you always get 0. So that one was easy. Let's do C2 now. Y squared dx minus x squared dy. So x is a constant here. X is constantly 2. If x is constantly 2, when we dx it, we get 0. And we're going to plug in x is constantly 2. And y is t, so dy is dt. So this is negative 4 from 0 to 4 dt. Whenever you integrate 1, you just get the length of the interval. So that's negative 4 times 4. It's negative 16. And then lastly, when we integrate over C3, y squared dx minus x squared dy, we are going to just plug in y equals x squared, like we did in example 2. So let's do that. Y squared squared is going to be x squared. Sorry, y squared is going to be x squared squared. Dx minus x squared, and then dy. Well, if y is x squared, dy is 2x dx. But we're starting off at 2 and we're walking to 0. So our bounds flip. All right, so this is the only integral with substance. We have x to the 4th and then minus 2x cubed dx. So that's 1/5 x to the 5th minus 1/2 x to the 4th, evaluated from 2 to 0. And this time when we plug in our upper bound, we are going to get 0. So we just have to subtract off what happens when we plug in our lower bound. And I'm going to cheat and not do this math and just look at what you get, and you get negative 72/5. So that's what each of the separate integrals are for each of these pieces. And when you encounter these, you do have to break it up like that. Well, there's going to be a way of circumventing this with Green's theorem, which I'll show you in a second. But the integral over c of y squared dx, the actual question is add these all together. So it's integral over c1 plus integral over c2, integral over c3. So that's 0 plus negative 16 plus negative 72/5, which is, oh shoot, this is 8/5 up here. Sorry, I cheated and I messed up when I cheated. That's an 8/5. Oops. It's an 8/5. And what we get here is negative 72/5. Moral of the story, don't cheat, just do the work. Okay, so that's what I believe you should get. Let's do this a slightly separate way now, and so you know, as far as this class is concerned, this is great. But we do have Green's theorem, as I indicated in the previous video, and it says if you integrate over a closed curve, something like p dx plus q dy, that's just the integral over the region it bounds, qx minus py dA. So the picture is this. You have a closed curve, you orient it counterclockwise, and your region's inside. So in this case, p is y squared, q is negative x squared. So this tells us that qx is negative 2x, and py is 2y. So the integral over c of y squared dx minus x squared dy is the integral over the region, which I'll go up and mark here. Well, I'll just reproduce here on the side. Just give me a second. Negative 2x minus 2y, because it's qx minus p dy, dx dy, or whatever order you want to write it. And remember, our region was that, where this was the squaring function. So r is the interior part. So what do we get? Well, if we integrate from x is 0 to 2, then y is going to vary from 0 to, if we take a slice of this, y is going to vary from 0 to x squared. So we can integrate from x is 0 to 2, y is 0 to x squared, negative 2x minus 2y dx dy if we wanted to. And I'm really hoping we get the same answer. All right, so we're integrating the first one with respect to y. So I guess my order is wrong here. Sorry, dy dx. There we go. All right, integrating with respect to y, we get negative 2xy minus y squared from y is 0 to x squared. Plugging in y equals 0 annihilates everything, so we just have to plug in y equals x squared. So we're going to get negative 2x times x squared minus x squared squared dx. And so that is x is 0 to 2. I think that's negative 2x cubed. And then minus x to the 4th dx, I believe. And so we integrate that, and let me give myself a little more space. We integrate that, and we are going to get, let's see, negative 1/2 x to the 4th minus 1/5 x to the 5th, evaluated from 0 to 2. Oof, I'm starting to get a little nervous here. And let's see, when we plug in 0, it annihilates everything. And then when we plug in 2, we get 2 to the 5th. We get minus 1/2 2 to the 4th minus 1/5 2 to the 5th. We don't have to subtract anything. Okay, how many 2's we got? I think we got a negative 2 cubed there, so that's like a negative 8. and then this is like a minus 32 fifths. And let's see, negative 8 is negative 40 fifths minus 32 fifths, and that's like negative 70 fifths. Oh, it's negative 72. Whew. Negative 72 fifths. All right, let's check. Moment of truth. Oh, baby. All right, so Green's theorem continues to hold, and this may or may not be. You might consider this conceptually easier or harder than the other one. It doesn't matter. You should be able to do these simple, relatively. The path integrals are simple, right? You just plug in and you compute. You should be able to do the path integrals, and if you want to appeal to Green's theorem, sometimes you can do that as well.